now we know how to make draw the molecules as best we can to represent their three-dimensional shape, and we know how to analyze their geometry. So when we get to the lab part, that's what we'll do for all the molecules. But let's also talk about polarity. So those two kind of go hand in hand. And the reason we talk about polarity after geometry is because you cannot determine polarity until you know the geometry of the structure. Because if you misidentify the geometry, you might still get lucky and get the polarity right, but probably not. And so polarity has to do with shifting electrons. And so the idea here is when I have a bond between two atoms, the bond really is not a line, right? A bond is a molecular orbital. It's an area surrounding both atoms, and also there's area between the atoms where that electron density is distributed. So the electrons in a bond are surrounding both atoms, satisfying both atoms' noble gas configuration. But the orbital is a pretty large space. The orbital, normally we think of an orbital as just surrounding one atom, like the 1s orbital, the 2s, right? This orbital is a molecular orbital. It doesn't just surround one atom. It surrounds more than one atom. And so the electron density can be distributed anywhere in that orbital. Right? Just like the electron density in a 1s, we just have a single hydrogen atom. We think of that 1s as being a compact sphere close to the nucleus. The reason we think of it as a compact sphere is because the vast majority of the density of that electron is distributed in that area right next to the nucleus of the hydrogen atom. When I have a molecular orbital, though, the electron density can be distributed wherever it's most stable. And since electrons naturally attract to protons, the negative charge of the electrons in that bond will be distributed wherever it can get as close to a proton as possible. And that will be determined by the electronegativities of the two atoms involved in the bond. Right? So one of my atoms has very little shielding or a lot of protons in its nucleus, then that atom will have a strong electronegativity. It will have a high electronegativity. It will be able to attract electrons well. So let's just say, for this example, the electronegativity of X was 2.1. The electronegativity of Y was 3.5. On a scale that goes from 0 to 4, that's a pretty big difference. The 3.5 atom is going to attract electrons a lot more. So if I were to really look at what that electron density might actually look like, if the yellow represents the majority of the electron density, it might look more like this, and then I might just have only a little electron density over here, but the majority of my electron density is around that atom. And so that's the result of electronegativity. When two atoms are sharing electrons, and they don't have the same electronegativity, the electrons will not be shared evenly between them. The electrons will naturally shift toward whatever atom attracts them more. And so if I've got extra electron density over here, what impact does that have? Well, the electrons are spending time over there, their electron density is over there. That creates more negative in that area because there's extra electrons over there. So that would mean I could show that by showing this area has more negative and this area has more positive. We use this symbol, lowercase delta, to indicate it's not a full negative. It's different from a formal charge. A formal charge would be if that atom actually is holding and having assigned to it too many electrons. Then it will have a formal negative. This atom probably doesn't have a formal negative. It just has a little extra negative as a result of bringing and naturally attracting more electrons around it. So the textbook focuses a lot on categorizing bonds as covalent, nonpolar covalent, polar covalent, and ionic. And that's useful. It's useful to use those categories to talk about the compounds. But really, those distinctions are not real. Okay? There's a spectrum of possibilities from completely nonpolar covalent to almost completely ionic and everything in between. These three categories are kind of arbitrary. It's just an attempt to kind of break that spectrum up into three sections. But there are examples all across that spectrum from examples that are totally nonpolar to examples that are just a little bit polar, so a little bit more polar, a little bit more polar. And then there are examples that are kind of in a gray area between polar, covalent, and ionic. So we're going to try to follow these categories, and I'm going to try to give you the best information I can about how to talk accurately about the behavior of these atoms and the types of bonds that they might experience. So a pure covalent bond or a nonpolar covalent bond would only be a situation where the atoms are equally sharing electrons, and that should really only occur when they have the exact same electronegativity. So the textbook focuses, unfortunately, on these cutoffs for the electronegativity difference from 0 to 0.5, and then from 0.5 to 2, and then above 2. I would like you to totally forget about that, because those cutoffs are arbitrary, and there are too many exceptions to that for them to be practical. It's not really fair to ignore differences in electronegativity less than 0.5. Because sometimes you could have individual bonds with electronegativity differences of less than 0.5 that only create really small partial charges, but if you have a bunch of those all adding together can create a pretty polar molecule. So saying that if the electronegativity difference is less than 0.5, it means it's nonpolar isn't really totally accurate. And in terms of the quiz question, most of you said, well, we're looking for a polar covalent bond, so the electronegativity difference can't be above 2. There are also exceptions to that. So using this 2 as a cutoff is not really a good idea. Because if I'm going to say anything with an electronegativity difference above 2 is ionic, and anything with an electronegativity difference below 2 is polar covalent, there's too many exceptions to that. There are a lot of ionic compounds that don't have an electronegativity difference above 2. And there are a couple covalent bonds that actually do have an electronegativity difference greater than 2. So if we want to look at these categories, the difference is really going to be in terms of, do the electrons need to be shared to complete a noble gas configuration or not? That is the question you want to ask yourself. If I give you a bond and I ask you to categorize it as covalent or ionic, what you want to ask yourself is, the atoms that are involved, do they need to share to make a noble gas configuration? If both atoms need to share to keep their noble gas configuration, it should still be covalent. If one atom is like one of these metals here in column 1 or 2, though, and it actually could make a noble gas configuration by not sharing, then it's not going to be able to share the electrons well, and the other atom should pull the electrons away, and that would make it become ionic. Okay? Yes?
So does this mean that if we don't follow this protocol here, we just, when we're thinking about nonpolar, are we only thinking about 2 elements that are in the non-metal section?
So let's talk about electronegativities. Yeah, let me answer that question. So the only time it's going to be totally nonpolar is when the 2 atoms sharing electrons are at the same element. That's the only time where they'll have the same exact electronegativity, and the electron density will be distributed right in the middle or evenly around both atoms. If this is symmetrical, I don't have any more red or blue on one side than I have on the other side, because the 2 atoms sharing the electrons are equal electronegativity. That's what creates a nonpolar. So anytime there's any electronegativity difference at all between 2 atoms, they're not going to share exactly evenly. So I shouldn't be calling that nonpolar. It should be at least somewhat polar. There are varying degrees of polarity, but if the 2 atoms have different electronegativities, and this is an extreme example because there's a big difference between hydrogen and fluorine, but even between hydrogen and carbon, hydrogen is 2.1, carbon is 2.5, the difference is 0.4, it's not a big difference. It's still enough to cause the electrons to shift a little bit more, at least a little bit more toward the more electronegative atom, and that may impact the properties of the compound. So then an ionic situation would be a situation where the electrons are not shared. And that should only be if one atom can't keep those electrons, because if by giving away the electrons to the other atom, it then makes a noble gas configuration. Right? So if we're thinking about sodium and fluorine, like here, I could think about them sharing. Thinking about sodium, right? It normally brings in, it's in group 1A, it has one valence electron. So it could take that one valence electron and share it with one of fluorines, and that would make a covalent bond. That's fine for fluorine because fluorine still has 8 valence electrons around it, including the shared pair. But for the sodium, it doesn't want 2 electrons. If it keeps its one valence electron and then picks up one more and shares with fluorine, that gives it the same number as magnesium. That's not a noble gas. So if you have a situation like that where one of the elements can only make a noble gas configuration by pushing the electrons away from it and not having those electrons, then it should be ionic. Because that is a situation where not only do we have a big electronegativity difference, but more importantly, the sodium needs to have a positive charge to have the same number of electrons as one of the noble gases. And so the fluorine will have a negative charge in that situation. And so most of the time an ionic bond will result from a metal and a nonmetal. Because it's always the metals that really need to give away electrons and not share in order to make a noble gas configuration. So that's why I have this slide here. There's no sharp distinction between nonpolar and polar. So that 0.5 cutoff is really not that useful. And there's also no sharp distinction between polar covalent and ionic. But we still have to do our best to try to put them into the categories that we have. So, but what I would like you to remember instead of those cutoffs of 0.5 and 2.0 is to recognize that if both atoms need the electrons to complete their octets, it will be mostly covalent. It might be very polar. There's a big electronegativity difference. It might be very, very polar. And that electron density might almost exclusively be only around one atom. But it will still be mostly covalent if both atoms still need the electrons to complete their noble gas configuration. Then both atoms will still have at least some of the electron density around them. It won't be completely ionic. If you have one situation where one of the atoms needs the electrons to complete its noble gas configuration, but the other atom can only make its noble gas configuration by avoiding sharing, then it will be mostly ionic. So examples of mostly covalent, a hydrogen-carbon, really any bond between nonmetals. Boron, hydrogen, fluorine, hydrogen, oxygen, carbon, silicon, fluorine. Anytime I'm dealing with both atoms being over here on the right-hand side, they're not going to be able to give up enough electrons to make a noble gas configuration. The only way they can make a noble gas configuration is by keeping the electrons they have and pulling more in and sharing them. And so those will pretty much always make covalent bonds with other atoms of the same type, other nonmetals. And so the examples that are mostly ionic, lithium, fluorine, you could have like a sodium carbon. The electronegativity difference between sodium and carbon is only about 1.5. That doesn't mean it's mostly covalent, because the sodium can't share those electrons and still make its noble gas configuration. It has to give the electrons away to the carbon in order to make its noble gas configuration. So that would be mostly ionic, where the carbon holds the electron density almost exclusively to itself. So let's look at a couple questions here from the textbook. 6.18. So in 6.18, they want us to categorize some of these. And we also have some up here, so let's just go through some of these. So the bond and the chlorine, bonded to fluorine, that's going to be polar covalent. They have different electronegativities, but they're both nonmetals, and they need to share to maintain both noble gas configurations. cesium bromide. So here I would find the cesium, which is way down here, the bromine, which is here. I don't even need to know their electronegativities, although they're given there. When I see that the cesium can only make a noble gas configuration by getting the same number of electrons as xenon, and it has to do that by giving away its electrons, I know it's not going to keep its electron and share. It has to give that electron away. So it's going to exist with a positive, which will make it ionic. In the C2H4, if we're specifically talking about the carbon-carbon bond, that is an example where I've got two atoms with the same electronegativity, so that should be nonpolar covalent. They have the same electronegativity, so the one atom is not going to be pulling any more than the other, so the electrons will be shared evenly between them, which is what nonpolar means. So a couple more quick examples, 6.18. We've got potassium oxygen in that compound. So what category would that fall into? Yeah, be mostly ionic. I don't even need to know the electronegativities. I just need to know that potassium, where it's at on the periodic table, it can't share electrons. It needs to give them away to make the same number as argon. The bond between the two nitrogens in the molecule N2, nonpolar. That's a nonpolar bond. Right? They have the same electronegativity. They should share the electrons evenly. So if I'm thinking about N2 and I draw the Lewis structure and I have it as a nonpolar compound, that's correct because there's no electronegativity difference between them. On average, the electron density will be spread out evenly over both atoms. Does that mean that the electron density will always be spread out evenly over both atoms at every moment in time? No. What is electron density? Do you remember that simulation we did where we had a positive charge and then we had all this blue around it, and then I used the cursor to grab that positive and move it to another location, and then as that happened, the electron density kind of like moved over there like a fluid sort of, and then followed it. That demo was, no, you don't remember? Okay, whatever. That demo was nice because it allows you to see that the electron density is fluid. It's not static. It will go to wherever there's a positive to attract it. And so this molecule, we think of the N2 as having the electrons being distributed evenly because it's nonpolar. That doesn't mean that at every single moment in time, those fluid electrons are always going to be exactly evenly distributed. There's a chance something else might come by, some other molecule might come near it that has the ability to attract electrons, and they might just kind of fluidly shift more to one side. There's also a chance that just through random opportunities, since the electrons are not static and they're just kind of randomly moving around in those orbitals, they might just spontaneously shift to one side a little bit more than the other side. So even a nonpolar molecule can become temporarily polar. But we do recognize we still label it as nonpolar because they have the same electronegativity. The average distribution of the electrons should be evenly distributed over both atoms. Any questions about that?
That yellow thing again, that was what?
That was meant to show that the electron density being fluid and able to move around and attract to different atoms. Okay, so what we just discussed was how do we analyze an individual bond's polarity? We can categorize an individual bond as nonpolar, polar, or ionic. We can also recognize for an individual bond, just looking at two atoms, the bond between them, if they have a different electronegativity, we know the electrons will shift toward whichever has a higher electronegativity. That will determine where most of the electron density is distributed. But we also want to be able to talk about what happens if I have an entire molecule with lots of atoms. Then where is the electron density distributed? Right, so that's going to determine, since most molecules have more than two atoms, we want to be able to analyze more complex molecules and talk about their behavior as a result of the electron shifting toward the more electronegative atoms in those molecules. So that's what we're going to talk about now. So first we're going to start off with a simple example. A very straightforward molecule with only 2 atoms. Whichever atom has the higher electronegativity is going to attract the shared atom, or shared electron. So the fluorine already has 6 electrons it owns by itself, but it's sharing 2, and since it's the most electronegative element, those 2 electrons are going to be spending their electron density or distributing their electron density more around the fluorine and a little bit in between, and maybe just a little bit around the hydrogen's nucleus. So the electron density is going to be much more around the fluorine. That's what this arrow is showing. So if I have a molecule and I want to show how the electrons are shifting in that molecule, I can use an arrow to show the direction they're shifting in. And I put a little tick mark here on the tail of the arrow to show that because the electrons are shifting away from that area, that side will become more positive, right? This looks like a positive sign there. Right, so that's the way you read that arrow. This is like a positive symbol. It's showing the electron density, the way it's shifting. That's going to create positive on one side and a little bit of negative on the other side. Another way to show the exact same thing would be to use these partial positive, partial negative symbols. Right? So they'll show where the electron density is being moved. Before we start to talk about more complicated molecules, though, let's talk about the quiz question, since that was more about individual bond polarity. So most of you said fluorine hydrogen, because the electronegativity difference is 4.0 minus 2.1 or 1.9. And if you were focused on what the textbook was saying with that 2.0 cutoff, that's a very reasonable answer, because that's pretty much as close as you can get to 2.0. And that is one of the most polar covalent bonds that you can have. However, one that is a little bit more polar would be the boron fluorine. That is 2.0 versus 4.0. So that is a difference of 2 instead of 1.9. So you might say, well, if the textbook was correct about the cutoff being a 2.0, and this is right on the cutoff, what is it? What category do I put it in? How do you answer that? That's why I'm saying you should not go with that description of the textbook, and instead look at the atoms that are involved. Is this boron going to make a noble gas configuration by giving away the electrons, so it becomes ionic, and the fluorine is the only one with the electrons? No, we already said that boron is not going to give away all its electrons and go down to helium, because that would create too much of a charge imbalance. It can't give away 3 electrons and take on a plus 3 charge when it only has 3 total positives, and if it only had 2 negatives, that would be a huge charge imbalance. So, sorry, I said 3. It has 5 positives. 5 positives and 2 negatives would be a very unstable charge imbalance. So, the boron has to share. So when I have 2 elements that really need to share to make their noble gas configuration, it should be covalent instead of ionic. So this is pretty polar covalent. And then if you look at the quiz I gave back, even more polar would be the silicon-fluorine bond. These bonds are really actually pretty stable as well. The silicon is only 1.8 electronegativity, and now compared to fluorine, that creates a difference of 2.2. So you would say, well, according to the textbook, that should be ionic, but it's not. The silicon, it will be bonding to other things, to make its noble gas configuration, but when it bonds to fluorine, that bond needs to stay at least somewhat shared, otherwise the silicon won't have a noble gas configuration. So that's going to be probably the most polar covalent bond that you could make. And if you take glass, which involves silicon and oxygen bonded together, and you add fluoride ions, it will eat right through the glass. Because the fluoride ions will come in, bond to the silicon, and push the oxygen out. Because the silicon-fluorine bond is a pretty strong situation where the electrons are shared between them.
Is that when glass is made, fluorine can destroy glass?
Yeah, fluoride ions will etch through glass or just dissolve glass.
Very good.
Yeah, so that's good information to know in case you need that. So you can also look at calculating quantitatively a dipole moment, so we're not going to focus too much on this. We're going to look more at trying to qualitatively compare the magnitude of dipole moments rather than actually come up with a number for the dipole moments. But if you wanted to come up with a number, how polar is a bond? It's going to depend on how much charge separation there is and also the distance between the atoms. This factor is more important. As a more relevant factor, we are going to simplify the situation and really pretty much only worry about that factor. So as we've been saying, the bigger the electronegativity difference between two atoms, the more polar it is. In actuality, it's not quite that simple, because the distance between the atoms is also a factor. But it's not usually enough of a factor to overcome the other factor, which is the electronegativity difference. So if you've got a comparison between two bonds, and one bond has a big electronegativity difference and the other bond has a smaller electronegativity difference, yeah, the distance between the atoms of those bonds might be a minor factor, but usually whichever has a bigger electronegativity difference should be a more polar bond. And so that's what we're going to use moving forward. And this illustrates that. Fluorine, hydrogen, bond length is pretty short. The shorter the bond length, the less polar it should be. But this is significantly more polar than the other one. And that's because the electronegativity difference is much bigger. So when I look at the HCl, the chlorine is only 3.0. So I've got the chlorine electronegativity difference isn't as great, but it's a larger bond length. Right, so the smaller electronegativity difference suggests it should be less polar, but the longer bond length suggests it should be more polar. So those two you could consider them kind of offsetting. But when we look at the actual numbers, we find the longer length of the bond is not really that important of a factor compared to the electronegativity difference. So if we just look at the electronegativity difference, that's a fair way to approximate and rank the relative polarities of bonds. So that's what we'll be using. We won't really worry about the bond length, but you should know that it is a factor. Then the book talks about percent ionic character. We're not going to get into the equation too much for that. It's a relatively straightforward equation. I'm not going to ask you to actually use it to come up with any specific numbers, but the reason I included it in here is to illustrate the factor that we already talked about, which is the fallacy of that 2.0 cutoff that the textbook talks about. If the electronegativity difference of 2.0 were really important, then you should see all of the ionic bonds on the other side of 2.0. But there are many examples of ionic bonds that have electronegativities of differences of less than 2.0. Right, so that's not really a very valuable cutoff. The real valuable thing is when I have atoms that are sharing electrons and they need to share electrons to make a noble gas configuration, that's going to be mostly covalent. If I have atoms that involve a metal and a non-metal, even if the electronegativity difference is only like 1.3, if the metal can make a noble gas by giving away the electrons entirely, then it will, and it will be mostly ionic. And so we could use this plot comes from using this equation and calculating how much ionic character there is in a bond versus how much covalent character there is in a bond. So we can see none of these ionic bonds are really 100% ionic. So even when an atom doesn't want the electrons because it needs to be without them to make a noble gas configuration, if the other atom has extra electrons, those electrons will still get into the outside valence level of the metal a little bit and start to share with it a little bit. There's still always going to be a little bit of sharing. So there's really nothing that is 100% ionic. And so, everything is kind of on this spectrum. Is really the best way to describe it.